Hi everyone, so today we're going to talk about the greatest common divisor, or the GCD of two numbers. And before we get there, let me just kind of remind you of a couple definitions that we had in a previous lecture. So the divisor and multiple. So a non-zero integer d, we call that the divisor of an integer n, and we write it using this notation that we're familiar with, right? D, and then you have sort of like this vertical bar. D divide, and you just read it as d divides n, right? This right here. Okay, so d divides n if there exists an integer m such that n is equal to d times m. So you kind of see right here, if you write n and you sort of factor it, so d is a factor, then we say d is a divisor. Okay, and then the notation, again, this is read d divides n. And if d is not a divisor, you could use this notation. Similarly, if d is a divisor of n, then you can also say n is a multiple of d. Kind of going back to the equation form of this, right? Anytime you see d divides n, you can always go to this equation. You see that that n is a multiple of d because there's a number that I can multiply by d by to get back to n. Okay, so just a really quick reminder there. So for example, what are the divisors of 6? Well, the definition just says that I'm looking for integers, right? So I actually have several, right? So -6, -3, -2, -1, 1, 2, 3, and 6. These are all divisors, right? Because every single one of these, I can write 6 as any of these times an integer, right? And then these ones are the positive divisors of 6. Okay. Now that's all talking about one integer, right? You're asking what are the divisors of that integer. But what if I give you two integers? I could actually look for divisors that are common among the two of them. And so we say a common divisor of two non-zero integers a and b is any non-zero integer that divides both a and b. So in other words, you're kind of looking for a d such that d divides a and d divides b. Okay, so that would be a common divisor among two integers, two given integers. Okay, and then the greatest common divisor of two non-zero integers a and b, we actually denote that by the GCD, so greatest common divisor of a and b, and it's the largest of all common divisors of a and b. So in other words, you're still looking for this same common divisor d, so you want to satisfy this first condition, but then you also want to satisfy this other condition down here, which says if you find another common divisor of a and b, so let's call it c, then c would have to be less than or equal to d. And again, this d here is the GCD. We denote that, the GCD, like this. Okay, so a quick example of this. Again, I could list out, let's compute the GCD of 6 and 4. Okay, so in other words, I could look at the divisors of 6 again. So I had -6, -3, -2, -1, 1, 2, 3, 6, and then I could also look at the divisors of 4, and the divisors of 4 would be -4, -2, -1, 1, and 2. And then what I could ask is, okay, among all of these divisors, among the divisors of 6 and 4, which ones are the common divisors? So the common divisors are, I have -2 as a common divisor, right? I have -1 as a common divisor, and I have 1 as a common divisor, and I have 2 as a common divisor. Oh, I'm missing. I forgot about 4, right? And 4 is also a divisor of 4. But those are all the common divisors, right? So the GCD, what you're looking for is among these common divisors, which one is the greatest, right? Which one is the largest, right? So that would be the GCD. So the GCD of 4 and 6 is equal to 2. Okay, so this is one way you could compute the GCD of two numbers. You could list out all of their divisors and then tell me which one among the common divisors is the greatest. In a little bit, I'm going to show you another method, and then in the next lecture, I'll actually show you another method. But the method that I'll show you today is actually quite efficient, at least comparable to listing out all the divisors. It'll be, I think, much more efficient than doing this. So let's move along. So remember that we had this division algorithm before. So let's just quickly review what this said. So if you give me two integers, and usually you assume a is not 0, but give me two integers and assume b is greater than 0, so it's a positive. Then there exists two unique integers, q and r, so that I could write it like this. So effectively, it's as if you're trying to divide a by b, and you get this quotient and you get a remainder. Okay, and then we knew these two conditions, that q and r are integers. Okay, so there exist unique integers q and r. And then one other thing is you actually know the remainder r has to be between 0, inclusive on 0, and b. But it can't be equal to b, so it has to be strictly less than b. And we call q the quotient and r the remainder. Okay, so we looked at this a bit, and we actually found some properties from this, and we explored like modular arithmetic and things like that. But looking at the GCD, I actually can get a kind of a nice little property here that will be very useful for us in just a second. So if you give me a and b are integers, and assume that they're both, not both of them are equal to 0, if q and r are the integers as above, such that I could write a is equal to bq plus r, then it turns out that if you want to compute the GCD of a and b, what you could actually do is you could compute the GCD of b and r. And what's nice about this is effectively what we're going to end up being able to do is we can kind of repeatedly use this division algorithm over and over and over again, and you will get a simpler and simpler GCD to compute effectively. Okay, so since this r has to be between 0 and b, do you see that over here these numbers are going to be smaller than the original numbers, like a and b? So you're kind of simplifying the problem, so I can kind of keep doing this over and over and over again. Okay, so I think it would probably be a good idea to actually look at the proof of this, because I think it'll go over some of the definitions and some of the techniques that we have seen in the past, as well as some of this new stuff. Okay, so how do we go about proving this? Well, first what we could do is these are things that you could theoretically compute, right? If I gave you a and b, you could compute it. Let's actually give them a name. So let m be equal to the GCD of a and b, and let n be equal to the GCD of b and r. All right. So what does this mean? Well, saying that it's a GCD, thus m would have to be a divisor of a, and m would have to be a divisor of b, right? Okay, I'll come back to this one in just a second. Let's explore this a little bit. Okay, so m divides a and m divides b, and it's the greatest common divisor. All right. So what can I write? I can write some equations, right? So this means that a is equal to mk, and b is equal to mj for some integers k and j. Right? Saying that m divides a says I should be able to write a is equal to mk, m divides b, b should be equal to m times j for some integer. Okay, so now I have these two equations, right, to work with. And what you're trying to connect between these two is our goal. The trick that I'm actually going to show in the end is I'm going to show that m is less than or equal to n, and then I'm going to show n is less than or equal to m, and that'll force them to actually be equal to each other. So it's not the most obvious thing how you would go about doing that, but what I'm going to do now is I'm going to use this other equation that we know is true and kind of combine this information together. So we also know a is equal to bq plus r. Okay. So what can I do here? Well, I can substitute. So now a is equal to mk and b is equal to mj. So I can write mk is equal to mj times q plus r, right? So just substituting for a and b here. Okay. Now, what do you notice? Well, I actually have two terms that have a factor of m in them. So what I can do is I can actually subtract this over. So I have mk minus mjq is equal to r. And now these two terms have a factor of m, so I can factor that out. K minus jq is equal to r. And this right here, since k, j, and q are all integers, this is an integer. Right? So what does this equation tell you? Well, if you stare at it a little bit, it shows you that m is effectively a factor of r, right? An integer factor. So m divides this r, right? So m divides r, right? Also, since m divides b, right, that was an original assumption, m divides b, and m divides r, what does that tell us? Well, m divides b and m divides r, but look up here. N was the GCD of b and r. So looking down here, I know that I have a common divisor among b and r. So this means m has to be less than or equal to the GCD of b and r, right? M divides b and m divides r, so it certainly has to be less than or equal to the GCD of b and r, okay, because it's a common divisor. It could be actually equal, but we don't know that yet. So thus, m is less than or equal to, and then I gave this a name up here as n. This is the only time we've so far used that name, n. Okay, so I know m is less than or equal to n. So I know that this GCD is less than or equal to the one on the left is less than or equal to the one on the right. Now let's show the one on the right is less than or equal to the one on the left. Okay, so similarly, since, similarly, up here, n is the GCD of b and r. So I know that n is going to divide both b and r, so I can write that out. So n divides b, and n divides r. And then I can do the same trick. So n is, b is equal to nl, and r is equal to n, and some letter we haven't used yet. Let's use h for some L and H that are integers. Okay? And now take this information and plug it into that same equation that we had before, that A is equal to B Q plus R. So now A equals BQ plus R, and I can substitute for B and R here. So I'll have A is equal to NLQ plus NH. And look, I already actually have that N is a factor here, so I can write LQ plus H, and this is an integer, right? This right here is an integer. So it looks like we're not really doing anything, but we actually are. Look at what you actually get. You get N is a divisor of A, right? So N divides A. All right. Thus, we have n divides a and n divides b, which was an original assumption. So together, this tells you n has to be less than or equal to the GCD of a and b. Because look at, n is a common divisor of a and b, so it's got to be less than or equal to the greatest common divisor. So that is, n is less than or equal to m. Remember that we named this m. So taking these two pieces of information, right? So what do we have? The first bit got us this inequality, and the second bit got us this inequality. So if you just stare at those two, look, I have m is less than or equal to n, and I have n is less than or equal to m. So thus, n has to be equal to m, and that is the GCD of, well, maybe I'll flip these, right? So m is equal to n, and then I'll actually get it in the correct, the right, exactly the same order. It doesn't matter because of symmetry, but I have the GCD of A and B is equal to the GCD of B and R, right? B and R. Yeah. Okay, cool. Now, why is that useful? Well, let me show you. Okay, so there are two pretty useful methods for computing the GCD. There really are three because I showed you the one up above where you just write out all the divisors, but that's kind of inefficient. This method here is very efficient. Okay, so this is actually called the Euclidean algorithm, so we'll call this also method 1 for computing the GCD of two numbers. So the short version of what this algorithm is saying is this two-sentence version. Okay, so use the division algorithm repeatedly until you get a remainder of 0, and then the last non-zero remainder is the GCD. Okay, well, that's not extraordinarily descriptive, so there is an actual algorithm that I'm following along here, but I think what would be probably best is to kind of explain it a little bit using an example. Okay, so let's do this example here. Okay, and then I'll kind of explain the algorithm. I'll explain what I'm doing, and then you'll look up above and we'll make sense of that that algorithm. Okay, so find the GCD of these two. So the way that the algorithm works is you take the bigger number and you divide that by the smaller number. I mean, one of them is going to be bigger. If they're equal, then it would just be itself, right? Okay, so you do this division, your classical method, right? So this 30 goes into this twice, and then you'd have to subtract 60, and you'd be left with 18. Okay, so from the division algorithm, this actually does give you a parallel equation that you could write over here. Maybe I'll actually do that. Maybe that's useful to actually see this. So from the division algorithm, right, another way of writing this is actually saying 78 is equal to 30 times 2 plus your remainder of 18, right? So the 2 here, your answer is your quotient, your Q, and the 18 is your remainder. Okay, so there is a parallel equation over here. Okay, now what's actually kind of interesting is what you can do is the way that this algorithm works is what you're going to do is you're going to take the previous number that you were dividing by, and now you're going to divide the remainder, divide that number by the remainder. Okay, so you can actually kind of organize this into a chain of long division. So I'm actually going to take the remainder from this one, and now I'm going to divide the previous b, by this remainder. Okay, so let's just work this out. So how many times does 18 go into 30? Well, only once. Okay, and I can subtract, and then now I get 12, and now this is my new remainder. Okay, and what you're going to do is you're going to keep doing this sort of successive division until you get a remainder of 0. So now I'm going to take 12, and I will divide by the previous number I was dividing by, which is actually the previous remainder. So it'll be 18. So this only goes in once, and now this quotient is 6, right? And then now I keep going, so I'm going to take the previous remainder, divide by this new one. Okay, now this one actually goes in evenly. Look at this. So this is 12, and I get 0, and so this is how I know that I'm going to stop. Okay, so I stop, and then here's the really cool part. Whatever the last non-zero remainder was, that'll actually be the GCD. So this right here is the GCD of 30 and 78. It's a pretty cool technique because all you really need to be able to do is some long division. So you could actually teach this to yourself back right after you learn long division, although you probably would have to explain what the heck this GCD is, but without knowing it, you could still actually figure this out. Okay, so let's look up here at what the algorithm says. Okay, so let a and b be integers. A is not equal to 0, b is positive. Find the GCD. What you're going to do is first divide the larger number by the smaller one. So that's what we did, right? We divided the larger number 78 by the smaller one 30, and you get an answer of 2 and a remainder of 18. So notice that the remainder, we'll call that R1, Okay, so we could actually label this if you want. Here, let me label this. So this is like your R1. Right? R1 and the divisor must have the same GCD as A and B. Well, that's what this previous theorem said. Okay, so this, or well, it was called a lemma. But the GCD of A and B is actually the same as the GCD of B and R. So coming down here, what that's actually saying is the GCD of these two numbers, the 30 and the 78, is the same as the GCD of 18 and 30. Right? This is like your B. Right? And this is your original A. This is your original A, and that's your first Q. Okay? Right? So this is A. Okay. And look at what you're kind of doing here. You're going to compute the GCD of 30 and 78, and what that lemma up above is saying is it's going to be the same as 18 and 30. So notice that the numbers are smaller. So you kind of keep doing the process. So now it says divide the original divisor, the smaller number that you were dividing by to find the GCD of, by R1 to get the remainder R2. So that's exactly what we did here, right? So divide B here by R1, and you'll get the next remainder, R2. Okay? Then it says, continue dividing Ri by Ri plus 1 until you get a remainder of 0. So you kind of keep doing this successive division that we were talking about. So this would have been technically R3. And this last one would be like R4. Okay? And then look up above here. It says, continue dividing until the remainder is 0. So this last remainder was 0, so that told us to stop. And then it says the last divisor, i.e. the second to last remainder, is the GCD, right? In other words, that's saying the last non-zero remainder, okay? So the second to last of all the remainders you computed. Okay, so kind of following that. We'll do a couple more examples, so don't worry. Now, each one of these has a parallel equation, right? So this second division, the second long division that we did here, has a parallel equation of 30 is equal to 18 times 1 plus the remainder of 12, right? 18 plus 12 is 30, so that looks good. And then the third one has an equation as well. It says 18 is equal to 12 times 1 plus the remainder of 6. And then finally, this last one, it's telling you that 12 is equal to 6 times 2 plus a remainder of 0, right? And then notice, well, first of all, that these are all correct, right? But actually what's kind of interesting is notice that each time the previous b and the previous remainder are kind of shifted over here. So you kind of see what's happening is the problem is that you're kind of reducing it to a simpler problem. And because of that previous lemma, the GCD is kind of preserved along the way. Okay, so that's kind of cool. And then the other thing that's really neat is you could actually use these equations over here to actually write the original two numbers, the 30 and 78, as a combination of the GCD. So I can actually write this number 6 as a combination of 78 and 30. And I'll show you that actually in just a second. Okay, so let's do this again. So let's compute the GCD of 102 and 18. Okay. So again, you could list out all the divisors of these things and figure out what's the greatest one, but let's use the Euclidean algorithm. Okay. So the method said to divide the larger number by the smaller number. So 102 divided by 18. So this goes in 5 times. 5 times 18 is 90. Okay, so then I have 12. Okay, so you do that. And then now you bring down the previous thing you were dividing by. So now I'm going to divide that by the remainder 12. So you get 1, and then a remainder of 6. And then now I'm going to divide 6 by the previous thing I was dividing by. Right, now this will go in evenly. Okay, and then the GCD will be this. You could say it's the second to last remainder or the last non-zero remainder. So this is the GCD. So the GCD of 102 and 18 is 6. Okay, so it's a pretty nifty process. You just really have to do long division. It's highly efficient as well. Okay, let's do another one. Oh, wait, I actually wrote the same number twice. Oh, that was a typo. Well, let's just fix that right now. So let's do the GCD of 305 and 122. Okay, so let's compute this. GCD of 305 and 102. Okay, so we're going to take the larger number and divide by the smaller number. So 305 divided by 122. Okay, this only goes in twice, which will be 244. Subtracting these is 61, right? And then 61 divided by 122. So that goes in exactly twice, right? So this is 122, and I get a remainder of 0. So this right here is the GCD. So the GCD of 305 and 122 is 61. Again, so just looking at this process, maybe look at this one, right? Do you notice that the problem is just getting simpler each time? Okay, so you're just going to have to do a bunch of them. I think I like to write it this particular way. The book writes it out in a different way, but I think that it takes up less space and you can kind of see the chain of division. It's fairly nice to write it in this particular way. This is kind of an exclusive for you guys. It's not in the book. Okay. Okay, and the last thing I wanted to mention to you is this really neat identity. It's called Bézout's identity. And what this says is that you could actually write the GCD as a linear combination. So what do we mean by that? Well, if A and B are integers and they're not 0, then it turns out that there exists integers x and y, so that you could write the GCD as a combination of those two, A and B's. So you could write the GCD of A and B as A times x plus B times y. Okay, and moreover, the GCD is actually unique. The GCD is the smallest positive integer of this form. Okay, so if you find other integers of this form, it actually turns out that there's another property that every integer of this form is a multiple of the GCD. Okay, so you kind of have to be a little bit careful when you're looking at this, but just because you find a combination of ax plus by, it does not mean that this is the GCD A and B. Okay, and if you also, the x and y in the equation are not actually unique themselves, so kind of read that theorem really carefully. I'll give you a couple examples to kind of illustrate this, but the first example that I wanted to show you was, could you look back at this example 3 here? So looking here at example 3, could we write this GCD as a linear combination of 30 and 78? So I already know that this is 6, right? Can you write 6 as a linear combination of 30 and 78? Okay, and the key to this is actually going to be to use these equations that we have over here. Okay, so let's bring those equations down here. Okay, so what do we have? Okay. Okay, so from example 3, we know the following equations are true. Okay. The trick to this is what you do is you actually solve for the remainders. Okay, so in these equations, so notice I can write 6 is equal to 18 minus 12 times 1, right? So solving for the remainder each time. And I could write 12 is equal to 30 minus 18 times 1. Okay, and then 18 is equal to 78 minus 30 times 2. All right. And then what you're going to do is you're going to start to substitute things. So 6 here is the GCD, right? The GCD of 78 and 30 is equal to 6. And then what I can do is I can slowly start to substitute this information in. So for example, I can substitute in the 12 and I can substitute in the 18 here. Okay, so substituting, we have 78 minus 30 times 2 for this 18 here. And then the 12, we can write that as 30 minus 18 times 1. Okay, times 1. Okay, and so I'll have 78 minus 30 times 2 minus 30, and then plus 18. Okay, but we're trying to write this so it's a linear combination of only 78 and 30. So I actually will have to substitute this 18 again. So I have 78 minus 30 times 2 minus 30 again. So there's 3 there, right? So times 3 minus 30, or sorry, minus 3 times 30, right? There's 3 of these 30. Negative 3 of these 30s, right? So negative 3 times 30. And then plus 18. So plus 78 minus 30 times 2. Okay, so combining these, I have 2 of these 78s. And then I have negative 5 times 30, right? Okay. And this is the answer, right? So this is 6 still. Okay, and look at what you have. You have written 6 as a combination of 78 and 30 here. So this is 78 and this is 30. These are the two that we were originally trying to compute the GCD. But look, you can actually write the GCD as a linear combination of these two. Now, Béziers' theorem, if you look at this carefully, it says that you're guaranteed you could find such x and y's here. So there will always exist them. It doesn't say that they're unique, though. There could be several of them. The GCD itself is unique. There's a 6 there, but there could be other coefficients here. Now, this solution method came from our Euclidean algorithm and the equations that we substituted in there. So this is a legitimate solution. Just note there may be other combinations of 78 and 30 to get the GCD. Okay, let me just give you an example. So indeed, for example, look at this. So you could actually write this as 7 times 78, and then you could add that to, well, you could subtract. But let me just write it as an addition, but it is a subtraction still. So negative 18 times 30. So look at this right here. So I actually still have a combination. Do you see that this is like your x and this is like your y, and they are integers just like they are here. Okay, they're combinations of 70 and 38. We say that they're linear combinations. Okay, so looking at Béziers' theorem, it's not saying that this x and the y are actually unique. It's just saying that they exist. And that turns out to be really useful. We will use this fact to prove several things in the next lecture, actually. But keep in mind the GCD is always unique. That's a unique number. Okay. The GCD, it turns out, will be the smallest positive integer of this form. So if you were to actually write out the collection of all possible linear combinations of these two, like 30 and 78, the smallest one would actually be the GCD, which is kind of another interesting property. And that can be useful for proving certain things. And then finally, if you find another integer of this form, it will always be a multiple of the GCD. So that's also kind of interesting.